Hi, this is Sanjay Bharti and welcome to TFiR Insight. And today we have with us Chris Mattmann, Deputy CTO at NASA JPL. First of all, Chris, thanks for taking some time out and talking to me today. And today we are going to talk about a wide range of topics, right?
Yeah, absolutely. It's been a long time coming. It's great to be on TFiR. Let's do it.
So before we start this interview, I would like to learn a bit more about yourself.
Well, I was born here in LA. I'm a Southern California person my whole life. I've grown up here. I've traveled the world. I like to tell people I went from the mobile home or the trailer to the PhD. I grew up poor in about an hour north of LA in Santa Clarita Valley. Was into sports, all the local LA teams, still hurting about Kobe Bryant and things like that. Was really into computers when I got to college at USC. Started to learn more and more about them. I haven't been the smartest person in the world, but I'll tell everybody that I'll outwork them. And that's how I, handle it. I work more than they do. So I'm really in sort of the last 5 to 7 years in technology and innovation. I have a PhD in computer science. I've been doing data science and analytics. I helped to create a lot of software that people in the world use, like Hadoop. I was one of the authors of Nutch, a web crawler that Hadoop came from. I've worked on digital forensics, uncovering, hidden wealth and money, working on the Panama Papers and things like that. Lots of different things. And so I have a lot of eclectic interests. And my latest passion du jour is machine learning, and hopefully we'll talk about that today. And at JPL, I love space. I manage the innovation team. It's about 50 amazing people. They're doing all sorts of projects, and we'll get into that.
Excellent. And I'm kind of honored to talk to you today. I wish we could do that in person, but let's just do it virtually. Let's start with the work that you're doing with the innovation team. Tell us a bit more about, what is this innovation team all about at the GPL lab?
We got lots of, interesting people there in science and engineering. My team lives in the information technology directorate. And, it's kind of interesting. We've built up a discipline, I'd say, of IT professionals over there that aren't just the people that say, deliver your phones or do networking and stuff. And those people are amazing, and we have tons of them. But my team is kind of unique. It's about people that do AI, machine learning, analytics, data viz, and they're really a cross-functional team. So we can hire the innovators, the people that, don't necessarily expect kind of the 30-year life cycle or, don't know where they're going to be in 30 years. We hire those people that really are doing things, that could be doing startups, that could be at the New York Times, that could be working at Facebook and, things like that. We hire those people and we provide them as sort of innovative consultants to science, engineering projects and missions. And so basically we pair them together with the domain scientists to do interesting work. We got people that are doing everything from looking at where today on Mars rovers, on basically on satellite instruments, we got radiation hardened processors that are as powerful as the good old iPhone 1, which isn't very powerful. And one of the challenges with that is that the computing, if you take a risk-averse process to that, which we do, we're the government, so we can't, crash things when that happens. It's a congressional inquiry and all that. And so in our risk posture, we'd like to fly things that are very tried and true. And sometimes that slows down on the computing that we can use. So today there are iPhone 1 RAD 750 processors running on space hardware and things like that. Tomorrow there'll be GPUs that are radiation hardened and stuff. And our team is helping to figure out the killer apps for that, the killer deep learning apps, so that instead of getting back 200 images a day from Mars, because it takes 8 minutes to go round trip Earth to Mars light time, maybe tomorrow you get back 1 million captions because we ran on board deep learning to caption those images and help scientists sort of believe in the results. So we got people that are doing that, got people that are doing data viz, analytics, that are working with, to communicate data science to people, lots of different things.
When it comes to all these projects, how much of the software is involved, how much of the hardware is involved? And you also mentioned, the machine learning is also, one of your, areas of interest. So when you look at all these missions, I was talking to somebody from CERN and I was like, hey, why don't we just use machine learning and AI and find all those planets? And his answer was simple, that with machine learning, you need to have models. We don't have models to train our machine learning to find those stars. We are collecting those models. So talk about these different components that are playing a big role in these missions. missions?
Yeah, so the engineering process basically tells us that we got to keep those things that you just talked about, software, hardware, and other things separate. And we do, at certain stages of it, but really it's all about breaking down barriers. If you talk about, and these are big in IT nowadays and stuff, cross-functional teams, putting people together, doing digital transformation, we don't want to keep them separate, especially when you're moving fast, in the early stages of a project, because keeping them separate might mean the difference between the project taking off or being used or being widely deployed. So we have what we call the Innovation Experience Center, or the IEC. Our people, we bring in the roboticists from our robotics division. We bring in the mechanical engineering, the people that are working on next generation materials. We've got data scientists from the business, looking at the business aspects of, what these parts are going to cost. Supply chain is a huge issue in the COVID era, and people thinking about where do we get all these parts from, or, and they think about the same thing with respect to spacecraft, especially in this era of small sats and CubeSats. So, we've been used to at NASA and in government and other space for so long. We've been used to basically a time in which it takes a decade or more, maybe 2 decades, to plan a big mission that's going to cost hundreds of millions of dollars to billions of dollars. All of the companies that we work with for parts and supply chain have been spec'd out through relationships for decades too. Except now in the modern era where we've got these CubeSats, small sats, these things that they're riskier. You can have more risk. Universities can put 3 of these on a payload, fly them up, and things like that. Well, NASA is in that business too, and we're, basically contributing to that. Well, the supply chain is totally different. The parts are different. The vendors didn't exist 5 years ago. These are some of the big challenges and things that we're looking at kind of in that environment. And then, we don't separate, in this environment, the people that are doing hardware. We're saying, hey, you want to have data-driven decisions there, right? You want to have testing data. You want to have hardware, related to that. We can help you do data science and analytics on it. Oh, by the way, you've got clean rooms where we're building the next generation hardware, like our Mars 2020 rover called Perseverance, which is on its way, to Mars, God willing, in July. And it seems like everything's going for that. It'll launch from here. Well, guess what? Here on Earth, terrestrially, we don't want to contaminate that. So in our clean rooms, we've got these big fat sensors, right? These $20,000 sensors that look at particulates related to that. There's only 3 of them on lab. They cost a lot of money. We don't get a lot of real-time analytics from them. What if tomorrow we could use small commodity air particulate sensors that are maybe within a percentage or two just as good? We can load the data up to the cloud, to Amazon, have a dashboard, make some predictions on it, and we could do it all for $50 or $100 or $200. So my team looks at a lot of those big sort of challenges and problems and visions the future for how we bring everybody together, at JPL and at NASA to do that.
As you mentioned, digital transformation, how much digital transformation has already happened at JPL Labs? Plus, how much role does software play in today's missions?
Yeah, so there's a huge digital transformation initiative at JPL right now. You hear digital transformation and people kind of wonder, are they talking about scanned papers or taking paper and getting it into bits? That's one part of it. And there's a big deal with that. We still have tons of physical papers, engineering drawings and diagrams that are, in the process of being scanned and things like that. We still have, data in our libraries and older mission archive photos and things like that are still in that process. And that certainly is one part of digital transformation, is literally digitizing data that isn't. And that's great. It has all sorts of clean environment implications. It's, all sorts of analytics implications. The other key thing is process-oriented digital transformation. Like, what are we doing today that could be automated? And I'm involved in a lot of conversations related to that. It's a big application of AI and machine learning. You hear the term intelligent digital assistants. These are, this is thrown out and people think of it as a boutique thing. Well, first off, it's about having frontline responders get self-serve faster. That is the initial biggest software use of an intelligent digital assistant for digital transformation. Take a process where someone has to wait to talk to somebody for 15 minutes, 30 minutes, 60 minutes. No one has time for that or wants it anymore, especially since they're all stressed out because of COVID and the pandemic and all that. How do we take those processes, turn them into, we put a chatbot, we give you some self-service, give you someone to talk to, and only hand you off at that point, after we have an intelligent digital assistant, to the frontliners after we've already served your self-service needs and things like that. So there's a lot of thought that's going on at JPL and at NASA for how we do things like that today. A lot of application of AI and machine learning in those areas.
You're talking about, using super expensive sensors and, move that workload to maybe AWS and all those things, and that could be super, inexpensive. What we have seen is that there's a lot of these open source technologies and all those, whether it's TensorFlow, whether it's AWS, the Microsoft and Google, they are releasing a lot of open source technologies that has made it very easy for data scientists, to work on these technologies. It's kind of almost commoditized where you can very easily leverage those technology without having big data centers and big machines. What do you think about it?
It's really democratized. I was actually just in a conversation with the head of Google TensorFlow project. He and I are talking a lot. Scott, we're doing a blog series together that's going to be coming out. And we're sitting here talking about BERT, which is a model to basically capture text, a text model, our brain's understanding of text, in a better way than, say, Bag of Words does. BERT has been trained on hundreds of millions of documents. But when you download the BERT model, that's trained on all those documents, you just get the model. You get the democratized power of Google and Facebook and all these companies that ran all this on the billions of documents on their servers. And then you today can download this in a Docker container to your laptop and run it. That's a great example, of things like that. And even more broadly, having these core frameworks and some of these core models are great. Now, the big challenge, and you touched on it earlier, is that in science, we don't necessarily have the BERT model for planetary image captioning yet. There's still a lot of work, that people have to do to kind of do what we call transfer learning or domain adaptation. Take these generic models that people are building, that are great on the Reuters corpus or all the world's data, for the news, and translate them into scientific speak or, the way an earth scientist talks or a geologist and things like that. And there's still a lot of work right now today that's done primarily with human labor, but I'm so excited, and we can talk more about this if you want here or later, about things like domain adaptation, zero-shot learning with less labels, because those are, in my mind, the next game-changing capabilities that we need to be working on. We need to cut down on the amount of labeled training data that we need to do this domain adaptation to really, really get it out there and democratize it.
First of all, just for our viewers, give a quick, very quick overview of that, and what are the challenges that you see with this?
Yeah, so the best way I could talk about like domain adaptation or transfer learning is sort of the following. The biggest investment in the world, if you're doing computer vision or object detection and things like that, has been in this big corpora that was created by many of the big web property companies called ImageNet. It was millions of images connected or collected across the internet of everything from dogs jumping to cars driving to birds to whatever, and then labeled with a really big, powerful word taxonomy called WordNet. This has been the data set that all computer vision researchers have worked on forever. It's probably $1 billion investment from many, many companies. No one is going to recreate ImageNet. And so when you apply models that are trained with machine learning that have been trained on ImageNet to things like images or things or data that it hasn't seen before, which is really the machine learning process, ImageNet has a really good understanding of everything ImageNet, or models trained with ImageNet have a really good understanding of everything ImageNet knows about, birds, cats, dogs. But when you apply it to, say, a planetary image of Mars, it's going to think maybe a dust devil is actually an elephant, because that's the closest representation it has. Just like your kid, when he sees or she sees Captain America like mine does, she initially called him Hulk because she hadn't seen Captain America yet. She knows it's kind of a superhero. It kind of has some similarities because that's the way our brain works, is trying to relate things from what it knows. So domain adaptation is actually taking all that investment in our, in computer brain models, which are neural networks and things, and you can imagine this with humans too. It's taking all that investment to build up that training, not wasting it again and retraining a whole new model. It's simply taking the thing that you think is, say, Captain America and saying, no, this is actually the Hulk. So changing the labels that you use for that. That's one common way of doing, domain adaptation and transfer learning. And so that's the type of thing that we're talking about. Don't recreate ImageNet. No one's got $1 billion or 10 years to do it. Take it, but then just provide that little knowledge that you need at the end to kind of say, oh, no, this is actually what it meant. It's actually a dust devil. Every time you see an elephant, it's a dust devil.
You mentioned it has been created for years by, all these web companies. Is there I don't know if there's a public domain, or is there any marketplace would be the appropriate terms where you can get these models?
Yeah, so right now the generic machine learning model for various like tasks or problems, like we call them, everything from object detection to text mining to say video recognition. These are kind of the popular public space data models. They're really broken down by framework. TensorFlow has its own model zoo. That's Google's offering. I'm writing a book on that. We've got things like PyTorch, which came from Facebook initially. They have their own what they call model zoo or places. There's a lot of compatibility between these frameworks. A lot of them have standardized on things like using the HDF5 format to capture all of, say, the tuned model weights, using standards like JSON or JavaScript object notation to capture what we call the hyperparameters or the input parameters to the model. So there is a lot of sharing. You can go between things like TensorFlow, things like PyTorch, things like Caffe, which came from the Vision Lab at Berkeley. These are kind of the major frameworks that are being used today. There's a lot of interoperability between them, and there's a lot of public models. What inevitably you have to do, and what people do, is domain adapt that to your problem. Is there a great library of all the world's domain adaptation and models? No. They're very specific. And as machine learning is democratized, we need to be thinking about how to kind of get them out besides other ways, which is the common practice, which is word of mouth, today and things like that. And so we're not there yet, but we're moving in the right direction, and talking about it and speaking on it like we're doing now will only help that.
Is there any collaboration going on between industry partners? I'm aware of Linux Foundation project is called Acumus AI, which is also kind of so is that relevant in that field, or is there any collaboration going on? Because in today's world, there is a saying also, if you want to go quick, go alone. If you want to go far, work with the foundation.
Yeah, there are collaborations like the Linux Foundation project that you mentioned. There's a lot of industry and science collaborations. A lot of the companies themselves that are providing offerings in this fashion. Sort of the next wave in this area is something I call, and the others call, AutoML. Auto machine learning. And what that is the recognition that the whole data science process, the machine learning process of building models, what we do as data scientists today is we look at a problem, we say, there's 3 or 4 ways of solving this. I might want to make a prediction. I'll use a classic regression. I'll try maybe an unsupervised support vector machine, or I'll try this deep learning approach to do it. And inevitably, there were 50 other ways you could have solved that problem where you needed to make a prediction. But you don't try them because you don't have time. And really, you can only try a few models, and then you tune those models because there's such a lot of effort in hyperparameter tuning and other things. Well, what AutoML is the notion that, hey, all those other approaches that you could have tried? Guess what? If we've got baseline solutions to problems, which we've got a ton for, why not just let the machine think up all the other possible solutions that it could have tried, rate them against criteria, which we have as well, which are, how accurate it is, how performant it is, and then just let the machine pick the best ones of the ones that we didn't try. So this is AutoML. Google's got an offering for this. There are other AutoML, like DataRobot is an emerging AutoML company. There are other AutoML offerings. So that really is democratizing more the notion of this industry science collaboration, bringing these model zoos out there. Since the machines themselves are the ones that are picking between all of these, that's really doing a lot. To kind of get it out there.
You use a lot of words there. Deep learning is there, machine learning is there, AI is there, AutoML is there. Since I'm talking to you, I do want to understand, depending on who you ask, they define what is the difference between artificial intelligence, machine learning, deep learning. What is the superset? What is the subset? Because sometimes, many times, the words get, all mixed up together.
I sound like I know what I'm talking about, don't I? Yeah, I mean, it's funny. A few years ago, for me, I'm a classically trained software architect. I studied software design, software architecture, some statistics, in college, unsupervised learning. I did some Bayesian decision making, kind of that area, so more statistics based. Over the last, 10 years, I learned some of this vocabulary and terminology. My best way to delineate it is sort of the following. AI is sort of what people think about when they think about Iron Man's Jarvis, sort of general intelligence and things like that. It's existed forever, but it hasn't been democratized because before, all the things that the researchers could think of to do AI were sort of inhibited by lack of access to powerful computing, lack of commoditization on it. I remember when I was in school, my AI class, I basically built a parser for propositional logic, for first order propositional logic. That's not AI. I was more parsing, but it was because we didn't have access to like big computers and what you needed, and there weren't software and frameworks to kind of do it nowadays. Machine learning is really, in my opinion, has been sort of really promulgated as an unsupervised way of really trying lots of models and building models to understand data, to make predictions, to group data together. And even though there's a big supervised and semi-supervised element to machine learning, when people think of machine learning, they typically think of that. They think, oh, well, you just put the machine learning algorithm at the data and it learns from it. Even though, and people are running into this today with machine learning, you need labels, because you can only learn so much from the unsupervised analysis, the exploratory analysis of data. Eventually, you're going to need labels, really strong predictions for it to learn. And when you look at the economy of that, it's very expensive today to do labels. Labels for cat videos, cheap, about $0.01 a label. Anyone can do that. Labels, again, I'm going to keep going back to that planetary science. Labels of what is a, planar bedrock right next to some veinous, potential water streams on Mars. Those labels cost you a PhD and 10 years of study, and probably the cost per label is about $10 a label. And when you look at models and how many of them we need and how much data we need, that's not economic. And so that's what people are running to with machine learning nowadays. Deep learning is really what people talk about when they're modeling the brain structure, and that's existed for a long time. Basically, people have looked at it. Really came out of computer vision. People looking at the visual cortex, looking at the brain, looking at the way that neurons fire and trying to develop a mathematical model for that. Those models have existed for 20 years. The real thing today that changed it has been the web property companies that made both the software to build these models more democratized and access to their computing. Once you coupled those things together and people could download and run these big models, apply them, make predictions, even train new ones using a laptop that maybe isn't a supercomputer but has enough computing power, that has been really the big thing. The problem in that area, real quick, is that you do all this work statistically in machine learning, AI, and things like that to model features, which are properties about data. You could spend your whole world just doing feature engineering. The thing that trips people out about deep learning is that these neural models, they're great, but it bypasses the feature engineering process, because at the end of the day, the brain and the model that you're building learns the features on its own for you, but it can't explain exactly what the features are. And so there's so much work today on, now that we've got these powerful deep learning models that think the way that we do, and the sky's the limit, going back and explaining why and having explainable AI, for them, because statistically we know a lot about the why, but they're not as powerful. These neural networks more powerful. We don't know as much about the why.
I don't think you can say sky's the limit, because you work at NASA. You multi-universe is not the limit, right?
That's a great point. That's a great point.
Yeah. You talked about the industry-wide collaboration. Is there any kind of collaboration between scientific organizations, also like NASA, JPL is there, then CERN is there, and European states, India's ISRO is there. Are you guys also collaborating not only to build the model, but also to share the resources that you have?
Absolutely. There's a lot of frameworks in science, especially the scientific community. You could argue what you want about them with technology, but one thing they've set up is an amazing framework to kind of collaborate. Just say planetary science. There's an international planetary data organization that collaborates both on models, AI, data sharing, and things like that. In Earth science, we have the AGU, the American Geophysical Union. We've got the Earth Science Information Partners Organization. So we have these frameworks where we don't have to wear necessarily our hats, even though I'm wearing mine, about necessarily where we work. We kind of can collaborate in a DMZ, a shared way, just people working on science and technology and bringing it together. So I would say there are effective forums for doing this across the sciences, no matter where you work. And really, I think part of our role as data scientists, machine learning people, and leaders in that domain is really just to kind of help, I think, people getting into the community or even established folks know what's real and what's not out there, and how to get the most bang for the buck. Because, this as well as I do, there's such a, machine learning is like the data science of today from, 5 years ago, or, 10, 15 years ago, the software architecture, the hot job, the sexy job that, and there's so much promulgation of things that, don't pan out because people are just learning things and putting them out there, which is great. really what we need to do is have highly curated and pointed at valuable kind of software, tech, data, and models. And so I spend a lot of time just pointing people at the things, that I think are that, and learning myself.
Before we started recording, we started talking about 3D printing, and because of this coronavirus COVID-19, there's a lot of stress on the industry and governments to provide those PPEs. Can you mentioned some work that you are doing, or you're involved with? Can you talk about that work to print these masks and all those gears?
Yeah, it's such a big issue right now. Our innovation team really spun up and worked with our mechanical engineering division and our robotics division when we were getting off a lab mid-March, when the stay-at-home orders went into effect in California, and as NASA responded and JPL responded to it. We have a lot of people that do 3D printing on the laboratory and that are very interested in it. We were bringing off equipment. IT was a big supporter at the front lines of doing that. And when we brought off some of the equipment, we brought off the 3D printers, and we were talking, what could we do to contribute to this? And we were seeing at the time a lack of personal protective equipment, or PPE. And we have a lot of people that deal with spacecraft that are, the 3M respirators, or these respirators, we actually have the filters on them. So not just the N95 filters, but like actual respirator HEPA filters and things, like these masks that look like, you're the Predator or whatever, when you're wearing them. We have a lot of people that work with those. Our big idea was we didn't want to disrupt the medical supply chain, but we wanted to see if we could use some of the 3D printers that we have to print out a couple different designs, because we had seen people doing that around the world. The people in Italy who were looking at the valves for ventilators, and JPL actually has a big ventilator project. There was a big press release about it yesterday, with the administrator and with Dave Gallagher, who's our strategic director, our director for strategic integration. Our little sub team just thought, hey, what can we do? And so we started looking to see if we could print a 3D designs for respirators. And so we ended up, we just went open source yesterday on the NASA-JPL GitHub. If you go to github.com/NASA-JPL, there's a COVID respirators project on there. We ended up building 3 designs, one for performance. We did form and fit checks on them, compared them to commercial COTS respirators. One for comfort, and one that's more conforming to your face, and so forth, using NinjaFlex and other materials that are kind of more squishy. And then we also provided custom filter designs where you don't have to go disrupt medical supply chains or whatever. You can get a vacuum bag, cut up the HEPA filter, get it in there in a kind of a custom housing and put it on a mask. So we've been sort of testing that with some close medical and other partners. We've been reaching out to other partners to kind of get these designs out there. They're not NIOSH certified yet, but we're working to do that as well. And so the designs are open source on our GitHub for NASA-JPL. And if your listeners or anybody is a guru with 3D printing like you can take a look and look for yourself. They're science-based. We're doing it based on science.
Before we conclude this interview, I also want to talk about, you wear so many hats, and one of the hats you wear is you're also author of, Machine Learning with TensorFlow 2nd edition. Talk a bit about that book.
So, rewind, a couple years ago, everyone on my team is talking about AI, deep learning, and machine learning. And I'm an information retrieval software architect, classic statistician guy. What the hell are people talking about? I wanted to learn more. And so I wrote about 10 years ago a book called Tika in Action with Manning. Tika is digital Babelfish. It's the thing that was used to analyze the Panama Papers, things like that. Because of that, with Manning books, I'm an author. I watch the books that are getting published. I saw a book called Machine Learning with TensorFlow, written by a guy named Nishant Shukla, who's a PhD graduate at UCLA, computer vision, doing great things in the startup community. His book was great. I picked it up. I started reading it. Nishant had this habit in that book, in the first edition, of everywhere where he started to teach you about regression or convolutional neural networks or autoencoders, he would kind of throw out a bullet at the end of the chapter. Oh, by the way, you might want to build a facial recognition network. And 8 weeks later, after I ended up doing a big graduate school assignment, and my wife was like, "What the hell are you doing up at night?" I'm like, "I see the future. I see what people are talking about. Machine learning." At the end of 9 months, going through that book, treating it like a big class, and I teach at USC too, so I know how to teach graduate computer science classes. I had enough material, really, in my mind, that filled all the gaps in that book, and enough new chapters and material for a second book. And that's what it is. We talk about in the first edition of the book, we talk about things like doing regression. In this version of the book, we talk about regression, and then I show you how to do a customer call center prediction where you can predict how much calls you're going to get for your workload, and we apply it to real data from New York's 311 service. In the first version of the book, we talk about classification. In this version of the book, I download and show you how to pull down all the IMDb movie review data and to build a sentiment classifier for it, and so on and so forth. So there's about 10 new chapters in this book. Each one of those is backed by Jupyter notebooks, shows you how to get the data. It shows you the ugly part of machine learning. You and I know this. 80% of the work is getting the data analysis ready and machine learning ready. I don't skip on any of that. I take you through all of that. Everything is runnable in Jupyter. It's all there, and gotten some good early feedback on it.
Thank you, Chris, for taking time out of your busy schedule and talking to me today. And I will look forward to continue this discussion on a regular basis, because AI ML is something that we are also increasing our focus on. So once again, thanks for your time.